Welcome students for this 11th lecture, and in this lecture we will discuss about an interesting term for the reactive power called instantaneous reactive power. And based on this power there is development of theory called instantaneous reactive power theory. So this point I have indicated in the previous class also, and if you remember that I have discussed that 1983-84 Achagagi and his group proposed the theory of or instantaneous reactive power theory. According to this theory, we define a term called instantaneous reactive power. Okay, and this is denoted by QT, similar to PT. But PT is not instantaneous active power. PT is simply instantaneous power. This term QT, which is denoted as instantaneous reactive power, has drawn much attention all over the world, and researchers have significantly focused on this issue, and they have given it different theories based on that. So we will discuss about this concept and extension for the instantaneous reactive power theory later on. So this concept of instantaneous reactive power is defined through alpha beta transformation. Okay, it is defined through alpha beta transformation. What is this transformation? This is transformation which transform ABC quantities into alpha beta, which are two mutually perpendicular axes. This is sometimes also called as three-phase to two-phase transformation, or sometimes it is basically called as Clark transformation, because first time it was developed by Clark. We can do in a most simplistic way, just looking the axis orientation and resolving the components of ABC along alpha beta. So we imagine that there is alpha axis and beta axis. Okay, we have denoted J beta down for sake of simplicity, but you can also take J beta up. So alpha axis and beta axis perpendicular to this. While as the axis ABC, they are 120 degree apart. So you can see this is A axis here, and this is B axis, this is C axis, this side. So I will put it here rather than this. This is B axis here, unit vector, and this is C axis. And then at any point of time, let us say at t is equal to t1, okay, at t is equal to t1, BA is equal to BA at t1. Similarly, this is BB is BB at point t1. Similarly, this is VC at point t1. So they have been located here. This is point A here, this is point B here, and this is point C here. They may have any value. So once we locate them, then we resolve their component along the alpha beta axis, basically along the horizontal and the vertical axis. So you can see that if we resolve B alpha, we resolve ABC along alpha, then you can see from here the BA along alpha is simply BA, and BB along alpha is BB by 2, because this is BB by 2. this is the magnitude of this, which is BB cos 60 in the opposite direction, and hence this is minus BB by 2. Similarly, we have the component of BC along alpha is this, okay, and this is nothing but BB cos of 60 in opposite direction, hence minus BB by 2. And then we have a beta. So beta is the components of BB and BC along BA, BB, BC along beta axis. Now as we see here, there is no projection of BA along beta axis because they are perpendicular coordinates, perpendicular axis. So this is a 0 here, you can see this is 0 here, and then we have component of BB along beta axis, which is cos 30 in the negative direction actually, but since we have taken this is a positive z beta axis, so this is plus root 3 by 2 into BB. So BB cos 30. On the other hand side, if we see it for the beta axis minus z beta axis, the component of VC along the vertical axis is this one here, okay, and this is again cos 30 of BC, or BC into cos 30, and it becomes again minus root 3 by 2 into BC. Alright, because this is in opposite direction, minus side. So these minus and plus sign will flip here, okay, these minus and plus sign can flip depending upon which side we take the beta axis positive. That is up to us. I just want to make the first positive then negative, so I have chosen this plus beta and this minus beta, but you can change it. It's not a big problem. Alright, now once we know this, we also define another component called zero sequence component. Zero sequence component concept comes from the symmetrical component. So those who have studied the power system or basic electric course, they would have studied also the symmetrical component. In symmetrical component, we resolve any unbalanced phasor, you can say BA, BB, BC, okay, and this can be transformed to a set of three sequence component, three balanced phasors, two balanced phasors and one zero sequence phasors, and they are called positive, negative and zero sequence component. Through this transformation matrix is called 1, okay, 1 1, 1 A square and 1 A square A. This is here 1 by 3 if you want, or 1 by root 3, and this is B0, B plus and B minus. Okay, this is called zero sequence, 0 for zero sequence. This is called positive sequence for negative sequence. And BABB could be unbalanced phasors. This is called phasor symmetrical component. Phasor symmetrical component. We can also have instantaneous symmetrical component. Okay, symmetrical component. In that case, we replace the phasor into symmetrical component. For example, B0, then B plus, B minus. Difference is small b, capital B, and capital B bar. So bar means phasor and small b means basically simply a instantaneous quantity. So 1 by root 3, 1 1 1 is called symmetrical transformation. 1 a square, 1 a square a. Okay, this is BA, this is BB, and this is BC. Because we have replaced the phasor with instantaneous quantities. Okay, instantaneous quantities. Hence, this is called instantaneous symmetrical component. Okay, so from this concept, we define a zero sequence component as B0 equal to VA plus BB plus BC by root 3. So we define B alpha, B beta and B0. For the time being, I will remove this. But remember, when we transform to set of variables to another variables, the power is always constant. The energy is always constant. And you know that the energy is proportional to signal square. For example, if you have inductance, the energy is half Li square, or it is B square by R, and so on. If you see mechanical systems, the kinetic energy is half mb square, okay, so and so on. So the point is that the energy of the signal, whether current, voltage, displacement, anything, is proportional to the square of the signal. Therefore, the power is proportional to the square of the signal, which I can say B alpha square, or you can say B A. In ABC frame, it will be BA square plus BB square plus BC square. In alpha plane, this will be equal to okay, so this energy, the power is proportional to the summation of the square of BA, BB and BC. So BA square plus BB square plus BC square. Similarly, this is proportional to B alpha square plus B beta square plus B 0 square. And therefore, there must be some constant for which that the energy, the power remains constant for both the systems, and which implies that BA square plus BB square plus BC square must be equal to B alpha square plus B beta square plus B 0 square. Okay, we will see and we can prove it that this is only true when there is a factor of 2 by 3 here, root 2 by 3. So root 2 by 3 here. And since the B0 is cannot be changed, so we still add for the symmetry of 2 by 3, but we also multiply by 3 by 2 root so that it is not affected, so that B0 is not manipulated. So this goes with this, and finally we will have by root 2 here. So this becomes by root 2. Okay, so for this factor we can prove that the square term, summation of a square term for both the sides are same. Okay. Can we prove that? Not very difficult. because we know alpha and beta, and we know V0, and we just square them and sum them. Okay, this 0 will go anyway, so I'll remove this also and put this bracket here. And root 3 by 2 is also common one way, so what you can do, we can still simplify it here, whole thing, and make it root 3 by 2. So this is root 3 by 2 BB minus BC. Okay, so these are three variables which we need to square to prove that the summation is equal to B alpha square, BA square plus BB square plus BC square. Okay. Well, it's not a very difficult if we go systematically here. Okay. So what is B alpha? So what is B alpha square now? I'll put it here. So B alpha square is nothing but 2 by 3 here, and the square of BA minus BB by 2 minus BC by 2, which is BA square plus BB square by 2 plus BC square by 2 by 4, not 2, because this is square, so this is not multiplication. So B alpha square will be 2 by 3 into BA square plus B square by 4 plus BC square by 4, then minus 2 BA BB by 2 plus 2 BB BC by 4, because by 2 into by 2, and then minus 2 BC BA by 2 this is the square of B alpha square, and plus B beta square. So I will put B beta square here. Take another color, B beta square. B beta square is 2 by 3 first, because it's root 2 by 3, and this is 3 by 2 means 3 by 4, so this into 3 by 4. Then in bracket BB square plus BC square and minus 2 BB and BC. We can simplify, 3 will go away with this, and this is by 2. So finally this becomes BB square by 2 plus BC square by 2 minus BB BC. Okay, so I will remove these terms here, and this becomes B square by 2 plus, so put below this actually BB square by 2, not here, and then plus BC square by 2, and then here minus BB BC. Also we can use 2 by 3 inside, bring 2 by 3 factor inside, so this becomes 2 by 3 A square, okay, and 2 by 3 if we put it here, then it becomes BB square by 6. Okay, So this factor becomes BB square by 6. So this is by 6, this is by 6, this is 2 by 3. Then this is again 2 by 3 factor. So 2 will go and become by 3 here. So this becomes 2 by 3. Similarly, the next becomes 2 by 3 here. So it becomes 2 by 3, you can say like this. So 2, 4, 4 go with this, we have only BB, BC by 3. So this all will go away, we will have by 3. And this is again minus 2 by 3, but multiply 2 by 3 factor. So become by 3. Okay, so this is the square of B alpha and square of B beta, B alpha square, B beta square. Now if we sum simply them, what do we get? B alpha square plus B beta square equal to two by 3 BA square. So this is 2 by 3 BA square. If we add 1 by 6 and 1 by 2, okay, it becomes 2 by 3. So this also becomes 2 by 3 BB square. Similarly, this also becomes 2 by 3 BC square. And then this is minus 2 by 3 BA BB. This together becomes 1 by 3 minus 1 becomes again minus 2 by 3. This becomes also minus 2 by 3 BB BC. And this is already minus 2 by 3 BC BA. Now what we will do here, we will add 1 BA square by 3 and subtract 1 BA square by 3. So this becomes BA square plus BB square plus BC square minus 1 by 3 take common. We will get here BA square plus BB square plus BC square minus 2 plus, this plus because minus is common, BABB plus BBBC plus BCBA. Okay, this whole thing is actually BA square BB square plus BC square minus BA plus BB plus BC by root 3 and whole square of that. Okay, whole square of that. And what is this? B0 square, 0 sequence component square. This side is B alpha square and B beta square. So we will bring this side here, then it becomes B alpha square plus B beta square plus B0 square equal to BA square plus BB square plus BC square. So you see the energy remains constant. Okay, the energy remains constant in both the reference frames, whether it is ABC or it is a alpha beta 0. We proved, but this happens only for the a constant of 2 by 3 that we have taken here. Okay. To make it common 2 by 3 for V0, we also divide by square root 2. And therefore, once we prove that energy is constant, now we can express the B alpha here, B beta, V0, through this matrix, 3 by 3 matrix, into BA, BV and BC. Okay. Now this matrix is 2 by 3, square root of this. This is here, alpha is 1 minus half minus half. So this is 1 minus half minus half. Beta is root 0, root 3 by 2 minus root 3 by 2. And this is 1 by root 2, 1 by root 2 and 1 by root 2. You can also express V0 first, it just rho will change. If I want to express the V0 first, okay, then we can change the row, third row into first row. So in that case, it will become like this, V0, B alpha, B beta equal to the same matrix 2 by 3 into this become 1 by root 2 here, 1 by root 2 and 1 by root 2. And this becomes here 1 minus half minus half. This is 0 root 3 by 2 minus root 3 by 2. Close this bracket. This into BA, BB and BC. Okay, this matrix is called alpha beta 0 matrix or 0 alpha beta matrix, depending upon that what kind of the sequence we use. Okay, so we can write this as A, 0 is first, so 0 alpha beta matrix into BA, BB and BC equal to B0, B alpha and B beta. Remember, all these variables are function of time, so we have denoted them by small letters. Okay, we have not used capital letters for them. Or simply you can write V0 alpha beta vector column vector equal to A0 alpha beta transformation matrix into, we'll get it BABC. So this is BABC. Same way we can express the current also. The same fashion we can express the current. So what we have done till now, we have expressed as B 0 alpha beta as A 0 alpha beta into BABC, and therefore we can also express as current 0 alpha beta equal to A0 alpha beta. Same matrix will come here and IABC. So we can resolve these ABC component into alpha beta, and these alpha beta 0 are kind of a mutually orthogonal components axis. This actually means I0, I alpha similar to voltage, I beta, 2 by 3, and this is same thing as 1 by root 2, 1 by root 2, 1 by root 2. What is here? 1 minus half, and 0 root 3 by 2 and minus root 3 by 2. BA, BB and BC. Now this matrix has very interesting property. Okay, this matrix, which is we call it A0 alpha beta, I ABC, I0 alpha beta. If we know this matrix, we can also find out IABC in terms of I0 alpha beta. So obviously we can use voltage or current. So we can write BABC therefore equal to A0 alpha beta inverse I or B here 0 alpha beta. Okay, and similarly we can use the current expression. We can express the current in terms of the voltage. For example, IABC should be equal to A0 alpha beta inverse IABC. We have to find out and see what is the inverse of this matrix and how this inverse is related to the original matrix. You try yourself. I will write the final answer that you will get after inverting this matrix. So you will see that this A 0 alpha beta inverse is equal to 2 by 3 root same factor, and in bracket it has elements of this matrix which are 1 by root 2, 1 by root 2, 1 by root 2. This is 1 minus half, and this is 0 root 3 by 2 minus root 3 by 2. This is the inverse of this matrix, and this is called as ABC because this transforms alpha beta components into ABC. So you can also write this is equal to ABC matrix into B0 alpha beta, or you can write down here ABC matrix into I0 alpha beta. So what is ABC? Is nothing but inverse of this matrix, but this is also equal to A0 alpha beta transpose. This is also equal to A0 alpha beta transpose. So this implies that this matrix has an interesting property that inverse of the matrix is same as the transpose of the matrix. This property can also be utilized to prove that power is invariant in ABC as well as alpha beta 0 transformation. We will see, we can very easily prove this concept that the power remains constant in both the transformations. For example, if you see here the power P3 phase as a function of time, instantaneous power, okay, will be nothing but, if it is constant in both the cases, it must be same as either BA into IA plus BB into IB plus BC into IC, and this must be same as V0 I0 or B alpha into I alpha plus B beta into I beta. You can take from any of the expressions. Okay, suppose I take in terms of the alpha beta. Okay, so if I take alpha beta, if I take this expression, I want to prove back that this is equal to VA into IA plus BB into IB plus BC into IC, then we can start with this itself. So this is actually called as inner product of voltage and current vector. This can be written in this form: V0 B alpha V beta. This into I0 I alpha I beta. Okay, this is called the inner product of voltage and current vector. V0 V alpha V beta transpose of this into I0 I alpha I beta. Okay, and what is this in terms of the ABC? It is a matrix A0 alpha beta into BA BB BC, the whole thing transpose, and then I0 I alpha I beta in terms of ABC is A0 alpha beta into I0 I alpha I beta column vector. This is further equal to, this is like AB matrix, so A transpose B transpose, AB transpose becomes B transpose A transpose, so this becomes VA BB BC, this is A here, this transpose, then A0 alpha beta transpose, then A0 from this A0 alpha beta, and then I0 I alpha I beta column vector. Now, as we have proved that the inverse of this A0 alpha beta is equal to transpose, so basically this is nothing but A0 alpha beta inverse. This is equal to A0 alpha beta inverse. So therefore, this will go away with this here. I can write here simply A0 alpha beta inverse. Now inverse into same matrix becomes identity matrix. So this becomes identity matrix I, and when I is multiplied both the sides, it gives the same product as BA, BB, BC transpose into I0, I alpha, I beta transpose. This is IA actually. So correct this. IA, IB and IC, not alpha. So this is IA, IB and IC. So finally this becomes as BA, BB, BC transpose IA, IB and IC, which is same as BA, IA plus BB, IB plus BC, IC. So we proved that the power, instantaneous power, either in alpha beta 0 or ABC is same. So this is B0 I0 plus B alpha I alpha plus B beta I beta. Okay, and with this understanding we are ready to define the instantaneous active power, instantaneous reactive power based on these concepts. Okay. In the next class we will learn that based on these products we define the term as PT, which is called instantaneous power, simply the inner product of voltage and current vector. Already we have expressed it. So this is actually nothing but B0 I0 plus B alpha I alpha plus B beta into I beta. This is also called the inner product of voltage and column vectors. So this is B0, B alpha and B beta transpose I0, I alpha and I beta. And the instantaneous reactive power is defined as the cross product. It could be like B alpha cross I beta plus B beta cross into I alpha. There is possibility of the I0 and B0 components, but it is assumed that these will be very negligent terms, hence the presence of I0 and B0 is being ignored here. Otherwise it will make the expression quite complicated. Later on you can consider those terms also. Okay. So we will explain more about them in the next class. We have understood how to resolve the ABC components in terms of the alpha beta components, and then based on that we also have ensured that the energy remains constant, and accordingly we have found the transformation matrix from either ABC to alpha beta or alpha beta to ABC. Based on these components we will make an attempt to define the term called instantaneous reactive power based on Akagi's theory proposed earlier for the development of the active power filters or for the compensation of the current and voltage using active power filters. See you again in the next class.